Now let's talk about multi-level paging. See, I'm going to take a big example, and it will be somewhat difficult, as I'm not going to say that it's really easy, but then I'll try to simplify it as much as I could. What I want you to do is, if you can understand it in first go, really good. Otherwise, even if you don't understand it, you please watch it 3-4 times, you'll definitely understand it. And what I'll do from my side is, I'll try to give you as many examples as possible, and then I'll explain the same topic. Okay. So yes, again, it is going to be difficult, not very easy, but try to put in full focus, and please watch it more than one time. Don't get worried, don't get panicked. It is easy once you understand it, but understanding it is going to take some time. Okay, fine. Now assume that the virtual address space is 32 bits. Virtual address space or logical address space. So what is logical address space? The size of the process, right? So let us say the logical address space is 32 bits. Now let us say this is the process. Okay, let us say the logical address space is 2 power 32 bytes, right? Assume that it is a byte addressable memory, and the logical address space is the logical address is 32 bits. Therefore the total size of the process is 2 power 32 bytes. And now assume that the page size is equal to 4 KB. So what does it mean? The page, the size of the page is equal to size of the frame is equal to 4 KB. Therefore the process has to be broken into pages, each of size 4 KB, right? If the entire process size is 2 power 32 bytes, and if the page size is 2 power how much is 4 KB? 2 power 12 bytes. Then how many pages do we get from this? We get 2 power 20 pages from this process. So if I break down the process into pages, the number of pages that I get in this process, right, is 2 power 20 pages. Now assume that the logical address space is equal to 2 power 44 bytes, right? Then what does it mean? It means that the entire main memory, it is not logical address space, it is physical address space. Physical address space is 2 power 44 bytes. Are the letters okay? Physical address space is 2 power 44 bytes. Therefore I am going to divide the entire memory. The entire memory is 2 power, main memory is 2 power 44 bytes, which is 16 terabyte. Okay, 16 terabyte is not a practical number, but then for this question these numbers make really sense. That is why I have chosen these numbers. Okay, so actually for 16 terabyte is not really practical. 16 terabyte of RAM is quite an exaggeration, right? But let's assume that 16 terabyte of RAM is available. Then we shall continue with this. Then I will be dividing the main memory into many small frames, and then how many frames do I get? Watch it. If total main memory is 2 power 44 bytes, and if the size of the frame is 2 power 12 bytes, then how many frames do we get? The number of frames I get is 2 power 32. If I get 2 power 32 frames, right, then how many bits are required to address each frame? How many bits are required to identify each frame? 32 bits. So keep that in mind. The number of bits which are used in order to identify a frame is 32 bits, right? So the number of pages in the process is 2 power 20. Then the entire concept is simple. We are going to take the frames, these pages, and we are going to load the pages into the main memory frames. So whenever you do that loading, when we load the pages into the frames, then we should be able to keep track of which page is loaded in which frame, isn't it? And sometimes it is quite possible that we might not load all the pages inside the main memory. We might load only the pages which we need now. Therefore we need to keep track of everything. In order to keep track of this, which page is present in which frame, so that later the conversion of addresses is simple, we are going to use the page table, right? And you already know that the page table will contain the number of entries, right? The number of entries in the page table will be equal to number of pages in the process, right? So the page table, I'm talking about the page table. Okay, now here the page table is going to contain how many entries? The number of entries in the page table will be equal to the number of pages in the process. Then how many pages are there in the process? 2 power 20. So 2 power 20 entries will be there. One entry will be representing one page, and now each page entry has to point to the frame in which that particular page is present. Are you following it? The process is having 2 power 20 pages, and all these pages can be loaded in the frames anywhere, main memory. Now this table should show at what location is each page present, right? Therefore the number of entries in this page table is going to be equal to 2 power 20, and each entry is going to point to a main memory frame, right? Saying that this particular page, let us say this is page number 0, 1, 2, 3, 4. Page number 4 is going to be present in frame number 0, 1, 2, 3, 4, something like this. Got it? And one more thing you should understand is a page table will never contain the page number. Page number is present outside, isn't it? It is just like an array. Array will never contain the array indices inside the array, isn't it? They will just be present outside, and what will be present inside it? The data that will be present inside should be able to address the starting of the frame or base of the frame, right? And now how many bits should be present here? So this number should be able to identify the frame number, isn't it? In order to identify the frame number, we need 32 bits, right? So this one will contain 32 bits. So 32 bits is nothing but 4 bytes, isn't it? So this page table will contain 2 power 20 entries, and each entry will be 4 bytes, right? Therefore, what is the size of the page table? This page table size will be equal to 2 power 20 is the number of entries, and size of each entry is 4 bytes. Therefore, the total size is 2 power 20 into this. So how much is this? This is 4 MB. Got it? So 4 MB is the size of the total page table. But what is the problem of this? The problem is the page size or the frame size is equal to 4 KB, right? And the page table size itself is 4 MB. Are you following it? Now the problem is this. Even this page table has to be present in the main memory in order to convert the logical address into physical address. But now if I have to put it in the main memory, the page table itself is so big that it cannot fit in one frame of the main memory. Then what should I do? Again, this page table has to be divided into many frames. Getting this? Now again, this page table has to be divided into many frames in such a way that many page table has to be divided into many pages in such a way that each page can sit in one frame. Then what I do is, I'll try to divide this entire page table into pages. Then how many pages are required in order to, how many pages can this page table be divided? Then the number of pages in this page table will be equal to page table size divided by page size, which is 4 MB divided by 4 KB, which is 1K. So 1K pages will be present in this one. Are you understanding this? So now I am going to divide into many pages, right, in such a way that the total number of pages present in this will be 1K. Got it? Now what I do is, I have to maintain the database again about which page of this page table is present in which frame of the main memory. For that reason, I need one more page table. It is going to be bit confusing here. Process is very big, so I have split it up into many pages, and then pages are loaded randomly into the main memory frames. In order to keep track of the original pages of the process, I am maintaining one page table, right? And next, the page table itself is so big, so I divide into many pages, and now these pages will also be loaded into the main memory frames. So in order to keep track of which page of the page table is present in which frame I have to go for one more page table. Okay, are you following it? Now I am going to go with one more page table, right? And now this page table will contain the number of entries, and these entries should be equal to the number of pages in this page table. How many number of pages are there here? Number of pages are 1k, right? Therefore the total number of pages here are 2 power 10. And now what should each page table entry, the total number of page table entries present in this page table are 2 power 10. What should each entry point to? Again, this entry should also point to one of the frames in which one of the pages of this page table is loaded, right? Therefore again this one will also contain 32 bits, a frame number, right? So at least how many? Okay, and one more thing, I am just ignoring the concept that the page table entry will also contain production bits and that dirty bits, reference bits, everything. I am just assuming that page table entry is containing only the frame number, the most important part. Okay, under that assumption, the size of each page table entry is going to be 32 bits, which is nothing but 4 bytes, right? So the total number of entries in this one is 2 power 10. So what will be the page table size? The page table size is going to be 2 power 10 into 4 bytes, which is nothing but 4 KB. Got it? So now finally the page size is also 4 KB and the page table size is also 4 KB. We are lucky, isn't it? Actually we are not lucky. I formed the question in such a way that we'll stop it at the 2-level paging, which means, see this is the first level page table and it is the second level page table. I formed it in such a way that we actually stop here. Okay, so we are lucky that, okay, we are not again lucky, it is a coincidence, or I framed it intentionally in such a way that we got only 2-level page table. Now if you observe this, the page size is going to be 4 KB and this level of page table also the size of it is 4 KB. Therefore happily this entire page table can go and sit in one frame. If you understood this, right? What I mean to say is this entire page table can now sit in one frame of the main memory and you need not divide it further. Then how is the logical address to physical address conversion going to happen? That is going to be complex. So if you understood this sizes, it is one part, and next we are going to go into the how to convert logical address to physical address. That is the second part. Okay, before going ahead, I just want to do some few things here. Okay, see this, now the logical address space is divided into pages, right? And how many bytes, and I assume that it is byte addressable. Byte addressable means finally whenever I generate a address, what is that I wanted to get is 1 byte, or whenever I talk about any address, I am talking about the number of bytes that are present in the system. Okay, so now since the page size is, one page size is 4 KB, how many bytes or how many addressable units are present in one page? 4 kilobytes, right? So in order to address or in order to identify one addressable unit in this page of the logical address space, how many bits are required? 12 bits, isn't it? So here I need 12 bits in the logical address space in order to identify one of the byte out of 2 power 12 bytes. Got it? And now coming to this page table, it is very, very important, just try to understand it. Coming to this page table, each entry size is 4 bytes, isn't it? Each entry of the page table size is 4 bytes. Then how many entries will be present in one page? That is what I am asking. Okay, see, the page table is divided into many pages, isn't it? Then what is that I am asking is, if every entry of the page table is 4 bytes, then how many entries will be present in each page? So how to do this? Watch it now. I hope that you have copied all this, right? See, what is that I want is, if each entry size is 4 bytes, right? Then how many bytes is how many entries will be present in one page, right? So one page size is 4 KB and each entry is 4 bytes. Then how many entries will be present per page? The number of entries per page will be equal to 1k, isn't it? 1000 entries will be there. Are you understanding this? See, each entry is 4 bytes and the page size is 4 KB, and I divided this page table into pages of size 4 KB. Then how many entries will go into one page? The number of entries that will go into one page is 1k. 1k is nothing but 2 power 10 entries will be present in one page. Then what is that I'll be interested in is, if 2 power 10 entries are present in one page, I'll try to always go into a frame and get one of the entry. If there are 2 power 10 entries in one page which will be loaded in one frame, then always I'll try to access one entry, isn't it? Therefore, how many bits are required in order to address one entry in this one page of the page table? 10 bits. So in this case I need 10 bits to address this. Okay, now watch this one. There is only one page, right? There is only one page. There is no need of paging here. I mean, paging is required, but then only one page is there. And how many entries are present in this one page? 2 power 10. So in order to identify one of the entry, in order to get into one of the entry, how many bits are required? 10 bits, straightforward. Got it? Then how will this entire thing make sense is, now given a CPU, right? If a process is running in CPU will have something called as page table base address, and now this page table base address will always point to the starting of the page table, which means it will point to the frame in which this page table will be present. Actually this page table, let's do one thing. Let's call it as page table 1 and let's call it as page table 2. It will be easy for me to refer, or sometimes they will call it this one as outer page table and this one as inner page table, because this one actually points to this and this one actually points to the process. That is how it happens, right? And now this outer page table should always be present in the main memory. Always the outermost page table should be present in the main memory in one of the frames, and this particular register will be loaded with the address of the frame in which this particular page table will be present. Therefore this particular page table will be present in one of the frames of the main memory, right? So it will be pointing, this address will be pointing to one of the frames. So in order to identify a frame we need 32 bits, isn't it? So this one will point to base of the frame, which is nothing but starting of the page table. You can just refer, I'm not directly going to show you there. Actually this is also present in one of the physical address, one of the frames in the physical address space, but I'm just showing you here to make the thing simple. Okay, and now whenever CPU, watch it, whenever CPU generates the logical address, how many bits is logical address there? 32 bits. Whenever CPU generates logical address, CPU always generates the logical address, isn't it? So what we do is, we want to go into this outermost page table which contains 2 power 10 pages, and we want to get one entry, right? If I have 2 power 10 pages here, in order to get one page among them, how many bits are required? 10 bits are required. Therefore the most significant 10 bits are used in order to get into the page table 1 and then get that particular entry, or get that particular get into that particular page number. Once I get into that particular page number, I can take that particular frame number, and again I'll go into the next one. Okay, watch it. What I mean to say is, using this page table base, I'll take this page table base and I'll append these 10 bits, some kind of addition. Then I'll go into the particular page table entry which I want to refer, right? And now this particular page table entry will point to one of the pages of the inner page table, isn't it? That is how we got it. So each entry here will be pointing to one of the pages of the inner page table, right? Now how many pages, how many entries are present in the page of the inner page table? If you look at the number of entries that will be present in the one page of the inner page table, they are already calculated to be 2 power 10. Then in order to identify them, how many bits are required? 10 bits. So the next 10 bits are going to act as index into the page of the inner page table, right? So I'll take these 10 bits and I'll do addition with the frame base, right, which I got from this, and I can get into one of the page table entries in the page table 2, right? And from this page table 2, what will come out? I'll get the base of the frame, right, which is pointing to the page which is of the process, right? So now finally the process page will be present in the main memory, isn't it? See, everything anyway, this one is also present in the main memory, this one is also present in the main memory, and this one is also present in the main memory, isn't it? So finally one page, one process will be present in one page of this process will be present in the main memory, right? Now I have to get into the corresponding word which I wanted, and I want to get it, right? Now getting the base of the frame is not just enough. I have to go into the frame and fetch that particular word. How many words are there? It is byte addressable, therefore how many bytes are there? 2 power 12 bytes are there. So in order to identify this, how many bits are required? 12 bits. So the least significant 12 bits is going to be used, right? I'll take the base of the frame from here and I'll add it to this, and finally by adding these two I can go to that particular byte and I can get it. Understood this? So this is how the entire procedure is going to work. See, if you didn't understand this, don't try to read it in the textbook. No textbook contains this explanation, I mean at least in this detail. So I know I have made it very clear. If you don't understand it now, what I suggest is you please watch this video over and again. You'll definitely understand it. Okay, I'll just summarize it. Watch it. So what I mean to say is, our process is containing 2 power 32 bytes, which means our process size is actually 4 GB, right? Then what I did is I divided into pages, then I got page table 1, then the page table 1 size turned out to be 4 MB, right? And 4 MB is also not fitting in one page. Actually page size is given as 4 KB, right? So 4 GB process doesn't fit in one page, therefore I divide into pages. That is how I got the page table 1. And now the page table 1 doesn't fit in one page because each page size is 4 KB, therefore I am going to divide into pages, then I get the second page table, right? And now this second page table turned out to be 4 KB, right? Okay, here I made the numbers in such a way that I get these numbers, right? Now it doesn't mean that always we are going to have only 4 GB. I mean, if process size is 4 GB, we get 4 MB and 4 KB. It is not like that. It varies from question to question, right? And now, in order to go to the particular word and fetch it, right, we have to go to the particular frame and then fetch it, right? Now the outermost page table is always going to be present in the main memory in some frame, right? So our logical address is going to contain 32 bits. Now how is this 32 bits divided is, the outermost page table, this page table 2 should always be present in the main memory in some frame. And how do we know in which frame that is present? For that reason, whenever a process is loaded, from the context of the process, we can even get the page table base. Now once we know the page table base, we know the frame in which the outermost page table is present. Now we'll go into that frame, and in that frame we have to go to the particular page table entry. Now here it turned out that the outermost page table contains 2 power 10 entries in one frame or in one page. In order to identify one of the entry, I wanted 10 bits. So the first 10 bits is going to act as index into the outermost page table. Now once I get into that index and once I get into that entry, what is that I get? I get the base address of the frame in which the page of the next level, which means I get the address of the base in which the page of this particular page table is present, right? And now if I go to that frame which is pointed by this entry, that frame at starting I have, but then I have to get into the frame and I have to get into the corresponding entry. Then how many entries are present in one page of the second page table, page table 2, that is again turned out to be 2 power 10 entries, right? Therefore the next 10 bits are used as going to be used as the entry into the second level page table. Now once I get into that particular page table entry, that is now going to point to the frame in which the actual processes page is present, right? But that is going to point me to the starting of the frame. Then in order to get into that corresponding word which I wanted, then what I try to do is I have to use 12 bits, because it is byte addressable and size of the frame is 2 power 12 bytes. So in order to identify one of the 12 bytes in that particular frame, I need 12 bits. So the total 32 bits is actually divided like this, and at every level we are going to add it. So if I take the base, page table base, and if I add this, right, then I am going to get the base of the frame. I am going to get the base of the frame in which page table 1 is present, right? In which base of the frame in which one page of the page table 1 is present, right? So you can call it as page table 1, page table 2, right? Page table 2 page base. Now if I take this and if I add this 10 bits, then I am going to get the base of the frame in which a page of the process is present. Now I take this number and if I add this 12 bits, then I get the actual word or the byte I am looking for, right? So this is how logical address is converted into the physical address. Got it? Okay, so finally, in order to run this process, what is actually required? One thing that is required is what is the page table base, which gives the the frame containing the outermost page table, right? So definitely this register is required, and then one page, this one, the outermost page table should always be present. Therefore we should definitely dedicate one frame so that it will contain the outermost page table, isn't it? And then now this outermost page table will point to one of the pages of the inner page table, and this one of the page has to be loaded in the one frame. If this is not available, we are going to load it into that frame, right? And now if we get into that frame and if we go into that particular entry, right, then that page table entry is going to point to one of the pages of the process, right? Therefore that particular page of the process has to be present in one frame, right? So in order to run this process, we need at least 3 frames, and all of them have to be present simultaneously. Maybe we could even do this in one frame. I mean in one frame, in the sense, first you load the outermost page table, right? Then you load it. It doesn't work with that way. It doesn't work. Okay. At least we need 3 frames, right? And these 3 frames, and since each frame is going to be of 4 KB, at least we need 12 KB, right? If I don't use this paging and if I don't use this multi-level paging, then what happens is I might have to use 4 GB process which has to be loaded in the complete memory, and I might need 4 GB memory to run it. But using this, I have drastically reduced the memory requirement to 12 KB. That is the advantage of using multiple page table. If I have only one level page table, then what happens? If I don't have 2 level page table, then what happens is still you could run it, no problem, right? But the problem is the entire page table 1 has to be present, which means it is containing 4 MB, so 4 MB has to be present. Okay, one more thing, 4 KB, 4 MB and 4 GB. You might think that what is the difference? It is just a small margin, right? But KB, MB and GB are actually numbers in 3 different spaces. You cannot compare them, or you cannot talk about them as if they are all same. Just to give you some example about how drastically these numbers are different and why we should save these spaces, I'll just give you one example. Watch it. See, if I have 1k seconds, 1k seconds, it is roughly equal to 17 minutes. That is how big the 1k is, right? And if I have 1 million seconds, this is roughly equal to 12 days. That is the difference. 17 minutes and 12 days is the difference between 1k and 1 million, right? And if I have 1 billion, which means 1 giga, if I have 1 gigaseconds, it is equal to 37 years. That is the difference between million and billion, which means 1m and 1g is that much different. Okay, so don't think that saving this, why are we doing all this in order to just save some small letters. G and M are not actually different in letters, they are different in two different spaces. One is 12 days. If I have 1 million seconds, it is 12 days. If I have 1 g seconds, it is a lifetime. 37 years is a lifetime, isn't it? That big it is, right? So using this multi-level paging, we could definitely save lot of space. At the same time, we need not have either entire process or we need not have entire process page table. Have one frame which holds the outermost page table, and then have one frame which contains one of the pages of the inner page table, and then have one frame which contains actual pages of the process, right? Yes, one more thing is, you are going to save the space but time is going to increase, isn't it? Why? You have to first access the outermost page table, and then access the innermost page table, and then access the process frame, right? It is going to give you 3 memory accesses, right? If I don't have this process, maybe I might have to just go directly get the word one access. One access is going to take how much? 4 GB space, isn't it? 4 GB space. If I don't have any page tables, if I directly load the process, one access is enough, right? But then it is going to take 4 GB space. But then if you want to save this space, you waste the time. So there is always a trade-off. But then loading the entire process without paging is going to hurt the multi-programming and the CPU performance. So always they go for this. And having just 3 frames is too small. What people do is they will try to assign some more frames. The reason is, if you have only 1 frame for each, then we should continuously be sending out a frame and again getting a new frame. If a process sends out one page and gets in one page for every instruction, then it is called crashing, which means for every instruction, roughly, if you try to send out one page and if you try to get one page for every instruction, then the memory access time or the access time is going to be equal to page fault time. What is page fault? Whenever a page is not present in the memory, we try to get it from the hard disk. That is called page fault. If we try to do it for every instruction, then the problem with such a method is crashing. That is called crashing. Crashing means doing lots of page movements without doing useful work, right? So having some particular balance, between number of frames allocated to a process and the page sizes, everything will actually help us in avoid crashing and will actually help us in save the memory access time, right? Anyway, we shall see some problems on that later. First, you try to understand this concept well. I'll do some more examples on this, using which you will be able to understand this well. You please watch this 2-3 times. Okay, fine.